Hi everyone. We're going to start today with the task of trying to compute some of these Laplace pairs that we're going to need to solve differential equations. And so let's go ahead and get started with that. We're going to start with a simple function called the Heaviside Function. You might not have heard it by that name before, but the Heaviside Function is a step function. It is equal to 0 for t less than 0 and equal to 1 for t greater than 0. So how do we calculate the Laplace transform of that? Well, first of all, let's just take a look at what this thing looks like. So if we had a set of axes here, then the function that we're talking about is one that is 0 up to 0, and then it starts being 1 afterwards, right? So the height is 1 there, right? So that is h of t. And a function that's going to be particularly important for us later, the main reason why we talk about the Heaviside function is because of the shifted Heaviside function, which is the same thing, but moved over by alpha time units. So if that's alpha there, then this is a function that's equal to 1 for t bigger than alpha, and it's equal to 0 for the lower numbers, right? So this is height 1 again. All right, and you might recall from calculus that when you take a function and you plug in t minus alpha, that moves it by alpha units to the right. Okay, so this is the Heaviside function, or the unit step function. It's this function that goes and then steps up 1 unit. So can we figure out the Laplace transform for this? And of course, we can, and we will. So how do we, let's do that down here. So the calculation is going to be, to find the Laplace transform of h of t, we need to take the integral from 0 to infinity of h of t times e to the minus st dt. Okay, so what does that mean? Well, h of t on this interval from 0 to infinity is just equal to 1. And so we're going to have, I'll go ahead and write this in terms of the limit, the proper way of doing this. The integral from 0 to capital T of just e to the minus st dt. And now this is a simple problem of just antidifferentiating. So it's the limit as capital T goes to infinity of minus 1 over s e to the minus st from 0 to t. And remembering, of course, that our variable for the integration is t, so that's why we get the minus 1 over s out there in front. All right, so plugging in, we have the limit as t goes to infinity of minus 1 over s e to the minus s capital T plus 1 over s e to the 0. That, of course, is 1. All right, so what do we have here? Well, this exponential will converge to 0 as long as s is positive. If s is 0, it's undefined. If s is negative, then this exponential will be positive, and this will not converge. So we only get a convergence, so the Laplace transform is only defined if s is positive. And we get that this is equal to 1 over s for s is greater than 0. Right, so that is the Laplace transform of the Heaviside function. Now let's look at the shifted Heaviside function. So it's the same kind of calculation. We want to know what its Laplace transform is. Then we just set up the same kind of integral. So we will be doing the Laplace transform of h of t minus alpha of s will be equal to the integral from 0 to infinity of h of t minus alpha e to the minus st dt. Okay, so what we know from just before, is that this Heaviside function is equal to 0 from 0 to alpha, and then it's equal to 1 from alpha to infinity. So this integral is really, the part from 0 to alpha is 0, so we can rewrite this as the integral from alpha to infinity of 1, just 1, times e to the minus st. All right, so rewriting that, this is going to be the limit as t goes to infinity of minus 1 over s e to the minus st, except now it's from t equals alpha to t. Okay, so plugging that in, we have the limit as capital T goes to infinity of minus 1 over s e to the minus st plus 1 over s e to the minus s alpha. And just as before, this term here will go to 0 for s greater than 0, and we get that this whole thing is equal to 1 over s e to the minus alpha s for s greater than 0. Right. Now this bit here, this multiplying by e to the minus s, is going to come up again. It's going to turn out that every time we shift the function by alpha units to the right, it just multiplies the Laplace transform by e to the minus alpha s. That's the shift operator. We'll cover that in the near future. Okay, so we can also notice that because the Heaviside function and the constant function 1 match on the time interval from t to t greater than or equal to 0, and that's the only time interval that matters for defining the Laplace transform, we know the Laplace transform now for 1. It's also equal to 1 over s, the same as the regular Heaviside function. So that's something that's going to help us out. It's going to help us out in particular in finding the Laplace transforms for power functions being functions like t to the n. Now, we can develop, using integration by parts, a very nice formula that relates the Laplace transform for t to the n to the Laplace transform for t to the n minus 1, and you can probably see that this is going to lead to an induction. So you're going to be proving this formula here on one of your homework problems, and then following it up to use induction to prove the Laplace transform or find out what the Laplace transform is for any power function. But I'm not going to tell you what that is right now because it's in the homework. No spoilers. You're going to have to work that one out yourself. Okay, so hopefully that will go well. Those are the last 3 problems that I've assigned in section 5.1. Okay, exponential functions, if we want to take the Laplace transform of e to the at, well, that's something that we did in the last lecture. So we're just going to recall that for the Laplace transform of e to the at of s is equal to 1 over s minus a for s greater than or equal to a. There is something to notice here, though, because what if we let a equal 0, then e to the at is just the function 1. And so this formula should match with our known Laplace transform for a equals 1. The Laplace transform here, we get 1 over s minus a, which is 0, so 1 over s. But we know already from just a second ago that the Laplace transform of 1 is also equal to 1 over s. So that's good. It works out. This is consistent. Even though we've calculated the Laplace transform for the same function in 2 different ways, we got exactly the same result. Now, I'm going to offer you a challenge here. So try to do repeated integration by parts to find the Laplace transform for sine of alpha t and cosine of alpha t. So remember, this is going to give you at some point an integral that looks like, right, you're going to be looking at sine of alpha t e to the minus st dt. This is the kind of thing that you learned how to integrate using implicit differentiation, using repeated integration by parts in Calc 2. So the key is to keep both sides of the equation, do the integration by parts twice until on the right-hand side you end up with something that also has this integral in it. You combine them together, and then you know what this is equal to, even though you've never really directly calculated it. So that's a trick that you're going to want to recall. See if you can do that. Okay, moving on. This is something that's going to be very interesting for us because we're trying to use Laplace transforms to solve differential equations. It's going to be important to know how to deal with derivatives when we're doing Laplace transforms. And we're going to cover this more in the next lecture, but let's take a look at what if we know that we have a function f of t, and we know it's a Laplace transform, and the derivative is still exponentially bounded, then what can we say about the Laplace Laplace, and a little misspelling there, the Laplace transform for f prime of t. Well, let's just work it out, see what we can figure out. We want to know the Laplace transform of f prime of t of s. Now, by definition, that's the integral from 0 to infinity of f prime of t e to the minus st dt. Now, we're going to try to figure this out, or try and get it in terms of the Laplace transform of the original function using integration by parts. We're going to let u equal e to the minus st and dv equal f prime of t dt. It should be hopefully pretty obvious why we would put f prime as our dv, because that means that v is equal to f of t, and our du is equal to minus s e to the minus st dt. All right, so plugging that in, we get u times v, so f of t e to the minus st. That's going to be evaluated from 0 to infinity, minus the integral from 0 to infinity of v du, so minus s e to the minus st f of t dt. Now, we have to look at this evaluation here. We have f of t e to the minus st. We're going to be plugging that in and letting t go to infinity. Now, because f of t is exponentially bounded, it's less than e to the alpha t, or e to the at, so this e to the minus st will cause the whole thing to go to 0 as long as if s is bigger than a, right? So we'll take a little time to think about why that is true, and then we'll plug in the 0 as well. So what we get here, just shortcutting the limit process, is we get 0 minus f of 0 e to the 0. From the integral on the right-hand side, we get plus, we can pull out this s here, so plus s integral from 0 to infinity of f of t e to the minus st dt. Okay, so now this whole thing here, this is just the Laplace transform of s by definition. So what we've arrived at is minus f of 0 e to, well, sorry, just minus f of 0, e to the 0 is 1, plus s f of s. So in the end, we've proven a formula, the Laplace transform of f prime of t of s is equal to s f of s minus f of 0 for s greater than a, where a is the exponential bound on the derivative. And so this formula turns out to be very useful in solving differential equations. So we want to keep in mind how that goes. So the interesting thing is that this one of the interesting things is that this incorporates the initial condition into the Laplace transform side of things. So we really are going to be able to solve initial value problems because it's going to translate information about the derivative and also about the initial conditions over to the transform side. There's also a nice little trick that we can do to try and figure out some Laplace transforms without actually computing the integrals. So for example, if we wanted to figure out the Laplace transform of sine of t, we can use the fact that we have the following relationships, that f of t is sine t. Now that's exponentially bounded because it's bounded, and its derivative is cosine t, and the second derivative is minus sine t. Well, that's going to be pretty useful. So let's say that the Laplace transform of f, we're going to call f of s, unsurprisingly. Now, what about if we wanted to find the Laplace transform of cosine t, right, which is f prime of t, by our formula that would be s f of s minus f of 0, but f of 0 is 0, so it's just s f of s. All right, now let's look at the second derivative, the Laplace transform of the second derivative of t, is equal to, well, it's just equal to the Laplace transform of minus sine t. By our result on linearity, that's minus the Laplace transform of sine t, right? It's a linear combination. So it's equal to minus f of s. So we're going to store that away for a second, because it's also true that if we want to take the Laplace transform of f prime prime, that's the derivative of f prime. So our formula up here applies here as well. It says that this is equal to it's equal to s times the Laplace transform of f prime of t of s minus f prime of 0. Okay, but we know that the Laplace transform of f prime is s times f of s. Right? We're going to use this here is equal to this. Right? So we're going to substitute that. We get s times s f of s minus f prime of 0 is 1. Right, so putting these two things together now, so this guy here, minus f of s, is equal to this whole thing here. They're both expressions for the Laplace transform of f double prime. All right, so we get minus f of s equals s squared f of s minus 1. So 1 equals f of s plus s squared f of s. Right, taking that over here, 1 is equal to 1 plus s squared f of s. So f of s is equal to 1 over s squared plus 1. So now we know the Laplace transform of sine of t. So this is a trick. Anytime you know relationships between the derivatives of functions, right? Some kind of relationship between a function and its own derivatives, also known as a differential equation, you can come up with a function for Laplace transforms based on that knowledge. So try that out with sine of alpha t or cosine of alpha t. It complicates things a little bit because we get some alphas showing up, but we get a general formula that's very useful. And we can add it to our catalog of Laplace pairs, which is what we're trying to build up right now. All right. Well,